the clean room floor using an Inside this smartphone are 62 microchips containing a total of 90 billion transistors. These microchips are incredibly powerful and the cornerstone of all technology. But how are billions of nanoscopic transistors manufactured into a microchip the size of a tiny ant? Well, all these microchips were manufactured in a semiconductor fabrication plant like this one. Inside it is a clean room, which spans the area of 8 football fields and is filled with hundreds of machines, ranging in size from that of a van to that of a city bus, and costing anywhere between a few million and $170 million. Within this microchip factory, silicon wafers travel from machine to machine and undergo around 1,000 processes over a 3-month period. And by the end of production, each silicon wafer will be covered in hundreds of CPU chips, each containing 26 billion transistors. When we zoom in, we can see the nanoscopic transistors at the bottom and over a dozen layers of wires above. This integrated circuit is then cut out from the wafer, tested, and packaged so that it can be installed into your desktop computer. In this video, we're going to explore the entire microchip manufacturing process and show you how billions of nanoscopic transistors and an impossibly complex 3D maze of wires are manufactured in one of the world's most technologically advanced microchip factories. It's an incredibly complicated process, so stick around and let's jump right in. A portion of this video is sponsored by Brilliant.org. There are 2 sides to understanding how microchip manufacturing works. The first is the sequence of steps and processes needed to build the nanoscopic transistors and the labyrinth of wires. Whereas the second is how the semiconductor fab and multi-million-dollar equipment of the clean room floor work. And we'll be flipping between these 2 sides to get a complete picture. Let's start by on the CPU and taking a look at what's inside. Here we have an integrated circuit, or die, which we'll refer to as a chip. This chip has 24 cores, a memory controller, a graphics processor, and many other sections. Within one of the cores, we can see its block diagram and the various elements. Zooming in on this multiply block, we find a layout of 44,000 transistors that physically execute 32-bit multiplication and constitute just 0.00017% of the overall 26 billion transistors in the CPU. Zooming in even further, we see layers of metal wires, or interconnects, and at the very bottom are the transistors that form the basic logic gates. Note that these layers of metal interconnects aren't floating, but rather the empty space that you see is filled with insulating materials, thus providing structure and preventing the metal wire layers from touching. Furthermore, here we're only showing the transistors at the bottom and 5 layers of metal interconnects, with vias traveling vertically between the layers. In actuality, there are a total of 17 metal layers of wires in the CPU, and each successive set of levels uses larger and larger interconnects. At the bottom are local interconnects that move data around this 32-bit multiply circuit. In the middle are intermediate interconnects that move data around the core, and at the top are global interconnects that move data around the entire CPU. You might be wondering, how small are these transistors? Zooming in again and past the interconnect layers, we find FinFETs, which are transistors whose channel dimensions are 36 by 6 by 52 nanometers, with a transistor-to-transistor pitch of 57 nanometers. Clearly, the transistors are incredibly small. Here's a mitochondria, a dust particle, and a human hair for size comparisons. Now that you have a sense of what the transistors and labyrinth of metal interconnects look like, let's explore how they're manufactured. We'll begin with an analogy. Imagine baking a cake that's 80 layers tall, with each layer cut to a unique shape. To make this cake, there are 940 steps in the recipe, which takes 3 months to complete and includes hundreds of exotic ingredients. And if any measurement, baking time, or temperature is more than 1% off, then the cake is entirely ruined. That's kind of what it's like to make a microchip. But microchips are even more complicated. Let's look at a single layer of this integrated circuit and run through a simplified set of steps used to build it. To start, a layer of insulating silicon dioxide is deposited on top of the wafer, and then a layer of light-sensitive photoresist is spread across the top. Next, using UV light and a stencil, a pattern is applied to the photoresist. Solvents then are used to remove the areas hit by the UV light, thus creating a patterned mask layer. Using the mask, the revealed silicon dioxide is etched away down to the previous layer. Next, the mask layer is removed, and a layer of copper is added to cover the wafer and fill in the areas that were just etched away. Finally, the surface is ground down and leveled off to reveal the copper and insulator patterns, and thus a single layer is completed. In order to build the next layer, which is a vertical set of metal vias, we repeat the same set of steps, but use a different pattern for the photomask. Since these layers are all built using the same set of steps, it's more effective to visualize the steps as a circle, like a clock. To build all the 80 layers of the die, this sequence is repeated over and over, resulting in 940 steps. One important note is that the FinFET transistors at the bottom are even more complicated than the metal wires, and thus additional steps are needed to fabricate them. Furthermore, cleaning the wafer to wash away dust particles that may have landed on the wafer, as well as inspecting the wafer to make sure everything is being built properly, happens frequently, and these steps need to be added to the circle. A different tool is used to complete each of these process steps. Now that we have an understanding of the steps, let's take a look at this semiconductor fabrication plant. This CPU is manufactured on a 300mm silicon wafer, which can fit 230 CPU chips. In contrast, DRAM chips are considerably smaller, and thus 952 of them can fit on a wafer. These silicon wafers are carried in stacks of 25 using a container called a front opening universal pod, or FOUP. This sealed plastic wafer carrier is transported around the clean room floor using an overhead transport system which lowers the FOUP onto the tool's landing pad. Inside the tool, robotic arms transport the wafer through vacuum load locks and to different process chambers where materials are added, removed, or processed in ways that we'll explore later. The wafers are then returned to the FOUP, resealed inside, lifted up to the overhead transport system, and carried to and dropped onto the next tool, where the next step in the process is completed. To build the entire chip composed of 80 different layers, it takes 3 months of traveling from tool to tool, where at each stop, one of the 940 process steps is completed. In order to increase the microchip mass production capabilities of a semiconductor fabrication plant, or fab, typically there are dozens of the same semiconductor tools organized in rows that perform the same process. On the clean room floor, there are a total of 435 semiconductor tools, resulting in the fab's production capacity of 50,000 wafers, or 11.5 million CPUs a month. These tools have rather complicated names, so we'll start by categorizing them according to their functionality. There are 6 groups: making the mask layer, adding material, removing material, modifying the material, cleaning the wafer, and finally, inspecting the wafer. We've color-coded the different functional groups to the various tools and process steps to help you not get lost. Let's next look at each of these semiconductor tools and see how they process the wafer in various ways. We'll start with the ones that are used to make the mask layer or the nanoscopic stencil on the wafer. These tools include the photoresist spin coater, photolithography tool, developer, and photoresist stripper. First, the photoresist spin coater applies a light-sensitive layer to the surface of the wafer and sends it through a soft bake, where the wafer is heated in order to evaporate the solvent from the photoresist. Next, the wafer goes to the lithography tool, which shines UV light through a stencil, which is technically called a photomask. The light passes through the stencil and is then demagnified or shrunk down to produce a nanoscopic pattern on the wafer. Wherever the light from the stencil touches the wafer, the photoresist is weakened. The wafer then goes to the developer and the weakened photoresist is washed away, leaving only the patterned nanoscopic stencil on the wafer. The wafer is then sent through a hard bake to harden the remaining photoresist. Next, the wafer travels to other tools to undergo processing. And once these processes are completed, the wafer goes to a photoresist stripper, which uses solvents to dissolve and remove the photoresist mask layer. And that's how a mask layer is formed and then removed. The photolithography tool is one of the most important, so let's take a look at it. Inside is a UV light source, a set of lenses to focus the light, a photomask which contains the stencil or design of the layer to be patterned, and a wafer carrier. The photomask is 6 by 6 inches and, based on the dimensions of the CPU, can fit 2 copies of a single layer of the CPU design. The purpose of using a photomask with these crazy optics is because it's a reliable way to copy and paste a design for billions of nanoscopic transistors and wires onto 230 identical CPUs on a single wafer in a few minutes. After the light passes through the photomask, the UV light goes to more lenses in order to shrink down the pattern by a factor of 4 and print a single layer of the design onto the photoresist. The wafer carrier steps from position to position, printing the photomask image at each stop until all 230 chips are patterned. Let's clarify one detail. In our previous examples, we talked a lot about this CPU having 80 layers. Specifically, what we were referring to is the number of photomasks and mask layers used to create all the different layers of patterns on the wafer. Therefore, one complete CPU chip uses 80 different photomasks, each costing $300,000. With only one mask layer being patterned at a time, this CPU chip will undergo 80 separate visits to the lithography tool. We could spend another hour talking about photolithography, but let's move on to the next category of tools. Deposition tools are used to add or deposit material onto the wafer. A lot of times we use the mask layer from the photolithography step to add materials to the areas uncovered by the mask layer, kind of like spray painting through a stencil. Due to the wide range of elements and compounds used to create the layers, deposition tools have a wide range of variations with complicated names and acronyms for each variant. But essentially, there are 3 key groups of materials that are added or deposited onto the wafer. Metals such as copper or tantalum, insulators which are typically called oxides, and crystalline layers of silicon. Each group of different materials uses different physics and chemistry principles to deposit the material on the wafer. and therefore has a different technical name for the tool that deposits the material. Deposition tools typically have a central wafer handling chamber, with the various chambers attached to the edges, dedicated to adding just a single element or compound. The next category of machines do the opposite, which is to remove material. There are two key methods. The first is etching. Etchers use either corrosive chemicals or high-energy plasmas to react with and remove materials from the surface of the wafer. They're typically used with the mask layer stencil in order to remove the material exposed by the mask, thus creating a hole that can be later filled by a deposition tool. The second method to remove material is CMP, which is chemical mechanical planarization. CMP applies slurry and uses abrasive pads to grind and polish away the top surface of the wafer, making it perfectly flat. CMP levels off the top layers of the wafer and is typically used as the last step in a cycle of processes in order to prepare the wafer for another layer to be added. The fourth category are tools that modify the silicon and are called ion implanters. These tools use the photomask stencil to bombard the unmasked regions with phosphor, boron, or other elements in order to make the P and the N regions required to form the transistors themselves. Therefore, ion implanters are only used in the front end of line. You might think that this is adding material. However, ion implanters only add around 1 atom of phosphor or boron for every 10,000 atoms of silicon. Additionally, while other machines spray paint a layer on top of the wafer, ion implanters hurl atoms deep into the silicon lattice, kind of like a cannon launching a baseball 6 feet into a concrete wall. This process typically damages the silicon lattice, which is why the following step is to repair the silicon by heating the wafer using a separate tool called an annealer. The fifth category of tools are used to clean and remove any contaminants or particles from the wafer. These wafer washers use ultra-pure water to clean the wafer and then dry it with nitrogen or hot isopropyl alcohol. Cleaning the wafer happens rather frequently in order to remove any stray particles that may have fallen onto the wafer. And finally, sixth are tools that inspect the transistors and metal layers for defects and are called metrology tools. A common metrology tool uses a scanning electron microscope with nanometer-level resolution to take pictures of the top surface of the wafer and determine if there are defects such as improperly patterned layers or particles on the surface. When fabricating an integrated circuit that takes 3 months to complete, it's important to repeatedly monitor the progress and make sure that each of the processes is being executed with nanometer-level precision. Now that we've covered each of the categories, here are the color-coded process steps along with the layout of the tools in the semiconductor fabrication plant. Let's run through the complete set of steps used to manufacture a single metal interconnect layer. First, a layer of insulating silicon dioxide is deposited onto the wafer. Next, photoresist.
Today we're going to talk about the project rock, paper, scissors below, all right? And paste the thing that we copy. Oops, I put here in upper. If it's working, so here I'm going to do a console.log hi, and we can tell I'm going to put rock, paper, and scissors, and I'm gonna create the script tag, okay, that we're gonna link with our index.js. So here we need to say the source index.js, okay, and that's it. If we save, this is it that we need for here, okay. In the index.js, I want to check if it's working. So here I'm gonna do a console.log hi, and we can test if this project is working so far. So I'm gonna open up the page, and I'll be right back. Now, like we can see here, I open it up the index.html. Okay, we're not gonna work with this anymore. And we can see here in the console.log that we have the hi, okay? So now we're going to start working with the project. Basically in here, what is the goal of this project? We're gonna play rock, paper, and scissors against the computer, and we need to get the computer choice. We're gonna get the player choice, and we're gonna play around, okay? And we're gonna count how many points we got in the game. We're gonna have 5 rounds, and we're gonna store our score and those things, okay? So the first thing we need to do is the get computer choice. So I'm gonna create a list here, an array called choices, options. So this will be all the options we have available, okay? So we can have rock, paper, or scissors. Scissors, okay? These are the options that we have. Then I'm gonna create the function. So we'll do function get computer choice. And this function, we have no parameters, okay? And right now I'm gonna do console.log computer because I wanna see if it's working. Computer, okay? And I'm gonna call the function get computer choice. Let's see if it's working. If I refresh in here, so you have to do Command Shift R or Control Shift R, and here we're calling the function get computer choice, and it's getting, okay? So now we need to get the choice of the computer using something that will make it random, a random choice, okay? So how can we do this? If you search for W3 Schools, that is a really good resource, we can use this math.render that will return a random number between 0 and 1, okay? This random here, it's gonna return a number from 0 and 1, and we can pick one of the elements that we have in our array, in our options here, okay? So we need to do a math. So what will be the math in here? We wanna select, I'm gonna create a variable here called const choice, okay? And I want to select one element in our arrays list, okay? So I'm gonna call the arrays here, the array options, and we're gonna use this math random, not the math floor, the math random. So this math random will return a number between 0 and 1, okay? But in our case, we have 3 elements, right? So we're gonna multiply by the number of elements, the length of this array. So we're gonna do math.random, okay? I'm gonna put everything here in a parenthesis, math.random, times the length of options. So we're gonna do options.length, okay? It will give us the length of this list. So basically it will choose a number between 0 and 1, for example 0.5 times the length of the options list, so 0.5 times 3, it will be 2, okay? It will be 1.5 actually, so 0.5 times 3, it will be 1.5, but we don't have an element 1.5, so we need to use this math floor that will give a number. Let's see here. So the math floor rounds a number down to the nearest integer. So for example, here we have 0.60, it will become 0, 5.1, it will become 5. So we're gonna use this math floor to give this random number, and it will round, okay? So we're gonna say here, math floor, and we're gonna round. All right, this is it that we have in here. So this is exactly what we're gonna do. Let's see what we're getting, okay? Because I think it's a little bit abstract 0.5, but we don't have an element 1.5, so we need to use this math floor that will give a number. Let's see here. So the math floor rounds a number down to the next d. It will become 0, 5.1, it will become 5. So we're gonna use this math floor to give this random number and it will round. Okay, so we're gonna say here math floor and we're gonna round. All right, this is it that we have in here. So this is exactly what we're gonna do. Let's see what we're getting, okay? Because I think it's a little bit abstract, right? So we're gonna do console.log choice and let's see what we have in our hands. I'm gonna expand this part, and if I hard refresh in here, it's saying now rock. So in every time we're refreshing here, it will give us a different choice, okay, for our list in here. Do you see rock, paper, rock? So it will generate a random choice in here. So instead of do console.log, here we're gonna return, okay, choice. So we want to return what is the choice that the user did. Okay, so far so good. Let me remove. I'm gonna let this in here. Now let's see the next step. So now here they are telling us to not do console.log but returning, so we're returning the expected output. Okay. Okay, for our list in here. Do you see rock, paper, rock? So it will generate a random choice in here. So instead of do console.log, here we're gonna return, okay, choice. So we want to return what is the choice that the user did. Okay, so far so good. Let me remove. I'm gonna let this in here. Now let's see the next step. So now here they are telling us to not do console.log but returning, so we're returning the expected output. Okay, now we're gonna write a function that plays a single round of rock, paper and scissors. So basically here we're gonna create now a function that will play the round. So here function, and will be play round, for example, and we're gonna receive the player selection and the computer selection. So here we're gonna receive the player choice and the computer choice. Okay, and what we have to do, we have to now check when we beats who we beats at each time. So to check who is the winner, I'm gonna create a function here saying check winner, for example, and I want to send the player selection and the computer selection. And what I'm going to do in here, I want to check if we have a tie or if someone wins our game. So how can we have a tie? If both of the players put the same thing, right? If we both put rock, scissor or paper. So we're gonna do if player selection is equals to computer selection, we want to return that it's a tie, right? Else if, so what is our next case? We want to check the cases where the player wins. So if player selection is equals rock, so basically rock wins when? So rock will always win when we have a scissor. So here we're gonna have computer selection equals scissor. Okay, what is our
is spread across the surface and the wafer is sent through a soft bake to remove the solvent. The wafer then travels to the photolithography tool, where the design from the photomask is transferred to each of the chips on the wafer by weakening the areas of photoresist hit by the light. The wafer next goes to the developer to wash away the sections that were hit by the light from the lithography tool, and then through a hard bake to harden the remaining photoresist. With the mask layer built, the wafer goes to an etching tool, where a plasma etcher removes a vertical column through the exposed silicon dioxide until it reaches the previous layer's metal vias. Next, the wafer is sent to a photoresist stripper, where the mask layer is removed. The wafer then travels
or other options, or in this case, response if goes in here. Do you see the wins? Selection. If we take a look, player selection is rock, and we can use a console.log in here to check. So the computer choice is rock, and change the value of I until how they're calling selection. So what are we gonna do? Now it's telling us true. So while this statement get validate is get playing us true, use prompt to get input from the user. So here, this is the prompt thing, okay? I'm gonna create a function called get function, get player choice, okay? It will be pretty similar to our function computer choice. Not pretty similar, but it's the same idea. So basically in this get player choice, we're going to do a loop and we're gonna keep asking the user for input. If the user doesn't give us a correct input, we're gonna ask again, but if the user gives us a correct input, we're gonna stop and continue, okay? So I'm gonna create a variable let validated input and I'm gonna set here equals to false, okay? And to do a loop, I'm gonna say while validate input equals false. So while this statement is true, while the validate input is still false, we're gonna keep looping. And what I wanna do, I wanna create a variable called choice, and I'm gonna ask the user for this choice. So we're gonna use this prompt. And here I'm gonna say rock, paper, or scissors, okay? Then we need to check if the user gave us something, if it's not empty, the input. So to check if it's empty, we're gonna say if choice equals no. So if it's empty, we're gonna say continue, because this continue means that we're gonna loop again. We're gonna do another loop, so we're gonna ask again the user for an input. Otherwise, if the user type in something, it's not empty, we're gonna convert this choice into all lowercase. So if the user prompt rock all uppercase, we're gonna convert everything to lowercase because it's easier to check with our options list, okay? Now we need to validate to check if the user gave us a validate choice, if the user gave us rock, paper, or scissor, or if the user gave us something else. So here I'm gonna create a constant called choice in lower, okay? And to do this, we're gonna use the variable choice, but how can we convert into lowercase? Here we have this function to lowercase, and basically the to lowercase will get the variable hello world that is all upper, and when we use here to lowercase, now it's all lowercase, okay? So we can use the to lowercase that will convert everything in lowercase. All right, so once we convert everything in lowercase, now we need to check if this choice is in our options list. So if the choice exists, if the choice is a rock, a paper, or a scissors, okay? And how can we do this? We're gonna use this JavaScript array includes. So basically how it works. Here we have a list called banana, orange, and apple, okay? And I want to show you. So here we have the list apple, banana, orange, apple, and mango. And when we use includes, it will check if the word mango exists in our list. Since it exists, it will return us true. If it doesn't exist, it will return us false. Okay, so this is exactly what we're gonna do. We're gonna say if options dot includes this function choice in lower. So if this is true, this means that our validated input is equals to, now it will become true, so we're gonna stop our loop and we will return the choice in lowercase, okay? This is what we have to do. And in here, we're gonna call the function get player choice, okay? So now this is pretty much what we need. So let's check. If I refresh in here, now it's asking rock, paper, and scissors. If I put here, if I don't put anything and I click enter, it will ask us again because we put here choice equals no, continue. So anytime we click enter and we're putting in nothing, it will ask again. If I put here Giovanna, it will ask us again because Giovanna, it doesn't exist in the options. It only exists rock, paper, and scissors. If I put rock all uppercase, it will accept, okay? I want to show you the whole page. It will accept rock, paper, and scissors. If I
to a physical vapor deposition tool where a sequence of metals fills in the exposed pattern and coats the wafer in metal. Finally, The wafer is sent to a chemical-mechanical planarization tool where the metal is ground down so that all that remains is a flat layer of insulating silicon dioxide and conductive copper interconnects that match the pattern from the photomask. A single metal layer is now completed, and the wafer is ready for the next cycle to begin, where insulating silicon dioxide in the vias will be added. Note that cleaning and wafer metrology or inspection steps occur in between many of these other steps. Furthermore, the process steps to make the transistors are less straightforward and utilize the ion implanter, and thus we'll cover them in a separate video on transistor physics and design. These steps are for building the integrated circuit on the wafer. However, there are additional steps in manufacturing a microchip, which we'll explore in a little bit. But before we get there, one important thing to note is that the semiconductor industry is incredibly secretive regarding the exact tool layout and the process steps and recipes used to make the transistors. We wanted to make the best video on how microchips are made, and it took us 180 hours of scouring the internet and textbooks for information and reference images. And, using what we found, we spent 205 hours modeling each of these tools, the many layers of the integrated circuit, and the semiconductor fab. Furthermore, writing the script took about 100 hours, and then animating all these visuals took more than 825 hours. As a result, this video took over 1,300 hours to make, and it's entirely free to watch. We want to make more videos like this one, where we explore computer architecture and how transistors work, and we can't do it without your help. The best way you can help is by taking a few seconds to scroll down, write a comment below, like this video, subscribe if you haven't already, and then share this video on social media or send it to a friend or colleague. Truly, just a few seconds of your time helps far more than you think. Additionally, we have a Patreon page where we'll be releasing behind-the-scenes footage of our work and updates for upcoming videos. If you find what we do useful, we would appreciate any support. Thank you. So then, what are the additional steps in manufacturing a microchip? Before chip manufacturing at the fab, we first have to manufacture the silicon wafers by refining quartzite into pure silicon, and then growing a monocrystalline ingot and cutting it into wafers. For reference, these 300 millimeter wafers are around 3/4 of a millimeter thick. They have a barcode on the side and a small notch in them to indicate the direction of the crystal lattice. Furthermore, these wafers are incredibly delicate and shatter into hundreds of shards when broken. A single wafer costs around $100, but after being populated with CPUs, it's worth closer to $100,000, making it quite literally 10 times more valuable than its weight in gold. Moving on to the steps after
put rock all uppercase, it will accept. Okay, I want to show you paper say equals to 0. Not just get player choice. We're going to, then we need a const, change the value of I until I is less than. Use the function we just, you win, return choice. Okay, 0.5 times 3 was less than, here we can say what is this, for example. Okay, and that's it. So now let's play a little bit with our code. So now let's and rock score computer ++. Okay, and we can 4 and we're 10, so now we lose because people beats rock. If I put here paper, enter, it will ask us again apple and mango, and when we use includes, it's something else. So here I'm going to create a constant continue. Okay, so I'm going to function play route function game. Okay, this is how they're calling here, game, and we're gonna use this for loop. Okay, so you can copy this for loop and we're gonna use in our code. So we're gonna do 5 loops. Okay, and what we're gonna do in each loop, we can prompt a message saying console.log. For example, before the loop, we can display a message saying, we can use console.log. Should say welcome, I don't know, okay. And in here, we're going to ask the user for, the player for a game, okay. So for example here, what I'm gonna do, I'm gonna say const player choice, actually player selection. And here I'm gonna say rock right now, okay? But then we need a const computer selection, and I'm gonna call the function get computer choice. So in every iteration, we're gonna ask what is the choice of the computer. Then we're going to make here, we're going to call the function play round, because the play round will tell us if we lose or if we win. So here I'm gonna call the function play round, and I have to pass the player selection and the computer selection. So this is exactly what we had before. Okay, but now inside of a loop. So let's see in here. If I refresh, I have to call the function game, okay? And if I refresh, here we have welcome paper rock, paper rock. So here actually I need to console.log, okay? I forgot, otherwise it won't display. And I will remove this console.log in here, all right? So what are we gonna do? Now if I refresh again, we're gonna see welcome. It's a tie, so in the first case, in the first case, computer selection was rock, so it was a tie with our player selection rock. Then we refresh. Here we have welcome paper rock, paper rock. So here actually I need to console.log, okay? I forgot, otherwise it won't display. And I will remove this console.log in here, all right? So what are we gonna do? Now if I refresh again, we're gonna see welcome. It's a tie, so in the first case, in the first case, computer selection was rock, so it was a tie with our player selection rock. Then we lose because paper beats rock, then it's a tie again. Then we won because rock beats scissor, and finally we had another tie. So it's working our game. Now we have to find a way of getting the input from the player. Okay, so how can we do this? Basically in here, they're telling us to use prompt to get input from the user. So here, this is the prompt thing, okay? I'm gonna create a function called get function, get player choice, okay? It will be pretty similar to our function computer choice. Not pretty similar, but it's the same idea. So basically in this get player choice, we're going to do a loop, and we're gonna keep apple, banana, orange, apple, and mango. And when we use includes, it will check if the word mango exists in our list. Since it exists, it will return if we both put rock, scissor, or paper. Computer selection will be equals. We can call this function and we check what is the return. Okay. And the else, this means that who is winning is the computer. So we're gonna return computer. Okay, so the good thing about this other function is that we're checking if it's a tie, if the player is winning or the computer. And here in the play round, we can just check, we can call this function and we check what is the return. So I'm gonna create a variable here, const response, result, for example. And we're gonna call the function check winner, and we're gonna pass the player selection and the computer selection, okay? Then we're gonna check what is the result. So if result is equals tie, what message we have to return here? So if it's a tie, we can say it's a tie. For example, we're gonna return it's a tie. No one, just it's a tie, you can check. Else if return result is equals player, so this means that the player won. So here we're gonna say you won, blah blah blah. So here we're gonna say return you won, you win. And we can say this paper beats rock. So how can we display what is the player selection or not? Here we can use backticks, okay? And the backticks will allow us to use parameters, so we can use variables in here. Do you see that even changed the color? So I want to say that player selection beats here, and we use again this notation, the computer selection, okay? So this way we're saying you win, rock beats scissors, for example. And the else, if the computer wins, we're gonna return you lost, you lose. And we're gonna say the same thing, but now the other way around. So computer selection beats player selection. So here we're gonna say computer selection beats player selection, okay? So basically this way we're checking who wins each round, all right? This part of the variation we're gonna see in a bit, but now let's practice a little bit with this case. Let's try it out with this that we're seeing right now. I'm gonna create a variable called player selection, and I'm gonna say rock. I'm gonna create a variable called computer selection. We're checking this important notice here. The computer selection, I'm gonna use the function we just made, the get computer choice. So
after chip manufacturing, the completed wafer is sent to a separate building where each of the CPUs undergoes rigorous testing to figure out if it works as intended. If a CPU works, that's great. But frequently, a particle or photomask defect has damaged a section of the integrated circuit, rendering that section defective. These semi-functional circuits are then categorized or binned based on what still works. These Intel 13th Gen processors are sold as an i9, i7, i5, or i3, depending on how many cores are functional with different product lines of CPUs whose onboard integrated graphics sections are defective.
So get computer choice, and I'm gonna do console.log, calling this function play round. So in the play round, I want to check who wins. I want to check if it's working. So we have to pass the two parameters, computer selection. Okay, so let's try it out. If I refresh in here, it's saying it's a tie. And why is that? Because if we take a look, player selection is rock, and we can use a console.log in here to check what is choice. So what we can do here, if I refresh. Here, the computer choice is scissor and the player choice is rocks. So rocks beats scissors, so we win because we are the player. So rocks beats scissor, and we're saying this message. If I refresh, we are rock and computer is paper. So here saying you lose, paper beats rock, okay? And we can keep playing until we have a tie. So the computer choice is rock and we have rock. Our choice is rock. So rock and rock, it's a tie, okay? So basically the play round is working. Now let's work with the next part. So now in the next part, we need to create a function called game, and we're gonna call the play round function inside of this one to play 5-round games. So basically, we're gonna use loop, like we can see in here. For I equals to 0, I less than 5, I plus plus. So basically in a loop, we will always keep, for example, in this case, where we'll be changing the value of I in each iteration, okay? And we're gonna change the value of I until I is less than 5. So we're gonna have at the first iteration, I equals to 0, in the second iteration, I equals to 1, in the third iteration, I equals to 2, in the fourth iteration, I equals to 3, and in the last iteration, I equals to 4. And then we don't need it. Okay, so far so good. Let me remove. So length of options, so we're gonna do right? Else result is equals. This means player selection is equal, and I want to send an example, and we're going to receive the player selection and the computer selection. So here we're going to receive the player choice and the computer choice, okay? And what we have to do, we have to now check when we beats who we beats at each time. So to check who is the winner, I'm gonna create a function here saying check winner, for example, and I want to send the player selection and the computer selection. And what I'm going to do in here, I want to check if we have a tie or if someone wins our game. So how can we have a tie? If both of the players put the same thing, right? If we both put rock, scissors, or paper. So we're gonna do if player selection is equals to computer selection, we wanna return that it's a tie, right? Else if, so what is our next case? We wanna check the cases where the player wins. So if player selection is equals rock, so basically rock wins when? So rock will always win when we have a scissor. So here we're gonna have computer selection equals scissor, okay? What is our other options? Or our player selection is equals scissor, for example. And so if we put scissor, the computer will lose when we put paper. Okay, so here computer selection will be equals to paper. Or the third and last case, if the player selection it's equals to paper, we win when when the other one has rock. So here we're gonna say computer selection equals rock. So if we have this case, this means that the player is winning. So we're gonna return player, okay? And the else, this means that who is winning is the computer. So we're gonna return computer, okay? So the good thing about this other function is that we're checking if it's a tie, if the player is winning or the computer. And here in the play round, we can just check, we can call this function and we check what is the return. So I'm gonna create a variable here, const response, result, for example. And we're gonna call the function check winner, and we're gonna pass the player selection and the computer selection, okay? Then we're gonna, here in the play round case, if the player selection it's equals to paper, we win when when the other one has rock. So here we're gonna say computer selection equals rock. So if we have this case, this means that the player is winning. So we're gonna return player, okay? And the else, this means that who is winning is the computer. So we're gonna return computer, okay? So the good thing about this other function is that we're checking if it's a tie, if the player is winning or the computer. And here in the play round, we can just check, we can call this function and we check what is the return. So I'm gonna create a variable here, const response, result, for example. And we're gonna call the function check winner, and we're gonna pass the player selection and the computer selection, okay? Then we're gonna check what is the result. So if result is equals tie, what message we have to return here? So if it's a tie, we can say it's a tie. For example, we're gonna return it's a tie. No one, just it's a tie, you can check. Else if return result is equals player, so this means that the player won. So here we're gonna say you won, blah blah blah. So here we're gonna say return you won, you win. And we can say this paper beats rock. So how can we display what is the player selection or not? Here we can use backticks, okay? And the backticks will allow us to use parameters, so we can use variables in here. Do you see that even change the color? Age all, use counts. If the score was less than, here we can say, what is the score? This is the score for the player. So here I'm gonna create score player, okay? And I'm gonna create a let score computer. I'm gonna say equals to 0. Here we're gonna check if winner and the else if. What will be our else if? This check winner return as computer. So check winner, player selection and computer selection is equals to computer. What are we going to do? We're gonna say here is not a score anymore, here is a score player, and here we're gonna say score computer plus plus. Okay? Then we need to check if score player is greater than a score computer. This means that we're gonna say console.log player was the winner, right? Because if we have more scores for the player than the computer, this means that the player was the winner, okay? Else if the score player was less than the score computer.
These wafers are transported to another building where the chips are cut out using a laser. flipped over and placed on an interposer, which distributes the connection points to a printed circuit board, while a protective heat-conductive cover is placed on the back side. The printed circuit board holds the landing grid array that interfaces with the motherboard, as well as various electrical components. Next, an integrated heat spreader is mounted on top, and the entire assembly is tested one last time before being packaged for sale. Finally, the CPU is now ready to be mounted onto the motherboard and installed into your desktop computer.
Const. We need to say let, because const, we can't change the value, but let is a variable that we can change the value. In every for loop, and we're gonna check who the score plus plus, all right? In the end, we can check, because we know that we're gonna have 5 rounds. If the score was less than, we're gonna have score plus plus. Won the selection is equals to player. This means that the player won the game. So we're gonna increase the value of score. So we're gonna do score plus plus, all right? In the end, we can check, because we know that we're gonna have 5 rounds. If the score was less than, here we can say, what is the score? This is the score for the player. So here I'm gonna create score player, okay? And I'm gonna create a let score computer. I'm gonna say equals to 0. Here we're gonna check if winner and the else if. What will be our else if? This check winner return as computer. So check winner, player selection, and computer selection is check winner, player selection, and computer selection is equals to computer. What are we going to do? We're gonna say here is not score anymore, here is score player, and here we're gonna say score computer plus plus, okay? Then we need to check if score the else if. What will be our else if? This check winner return as computer. So check winner, player selection, and computer selection is equals to computer. What are we going to do? We're gonna say here is not score anymore, here is score player, and here we're gonna say score computer plus plus, okay? Then we need to check if score player is greater than score computer. This means that we're gonna say console.log player was the winner, right? Because if we have more scores for the player than the computer, this means that the player was the winner, okay? Else if the score player was less than the score computer, this means that the if it means that we're gonna say console.log player was the winner. Or then we need, and here we're gonna say score. Say here is not is equals to computer. What are What we're going to do, we're gonna say here is not score anymore, here is score player, and here we're gonna say score computer plus plus. Okay, then we need to check if score player is greater than score computer. This means that we're gonna say console.log player was the winner, right? Because if we have more scores for the player than the computer, this means that the player was the winner. Okay, else if the score player was less than the score computer, this means that the computer was the winner. Computer was the winner. And the other case, so if they are the same, so else, this means that we have a tie. So here we're gonna say we have a tie, for example, okay? And that's it. So now let's play a little bit with our code. So now let's play around with our tie. So here we're gonna say we have a tie, for example, okay? And that's it. So now let's play a little bit with our code. So now let's play around with our code. One thing that I wanna do is every time we finish the console.log in here, I wanna do a console.log and I wanna create like some spaces to check to say that we are in a different round, okay? So now let's play around. If I put here paper, it's saying you lose, scissor beats paper, so now we're going to a new round. If I put here paper again, we lose again. If I put here rock, we lose again. If I put here scissors, it's a tie, and if I put here rock, again, we lose. So it's saying game over, computer was the winner. So we basically lose 4 times and we had a tie. If we run it again, if I put rock, so we lose, rock, we won, rock, rock, and rock. So now we have 2 winnings, all right, 2 ties, and now it's saying game over, player was the winner, okay? So it's basically that we need to do. We just need to worry about the JavaScript, okay? So once you finish, you just need to submit all of these changes. So what you can do here, you can click stage all, you can say start and finish game, okay? We can commit this file, and now we just need to go here to, do you see this number 2? We're going to click in here and we're gonna push to origin, okay? Now if we take a look at our GitHub, if we take a look here in our GitHub and we refresh, now we have here the start and finish game, set up HTML and CSS. So it kind of did everything in 35 minutes. Just to finish, you have to go to your settings, click in pages, and here you have to change the branch to main and save. It will appear on your computer in 1 hour, so once it's done, you'll have your website for everyone, okay? So now, like we can see in here, it's working, okay? We have here in our GitHub, so this is it for our project, all right? If you enjoyed this content, please give us a thumbs up, subscribe to our channel. If you have
as well as various electrical components. Next,
I'm
an
running something called
integrated heat spreader is mounted on top, and the entire assembly is tested one last time before being packaged for sale. Finally, the CPU is now ready to be mounted onto the motherboard and installed into your desktop computer. It's important to understand that chip manufacturing requires an incredible amount of science and engineering, and there's a free and easy way to learn the basic principles inside each of these complex tools. And that's with this video's sponsor, Brilliant.org.